Alrighty, hello everybody. I hope that your spring break was nice, well rested. Um, Welcome to spring term. This week we're going to be starting off with respiration, and awesome. I'm going to go ahead and get started. I also wanted to say thank you guys for being flexible with my ever-changing schedule. I really wanted to keep things consistent this year, but unfortunately my class schedule just kept kind of getting in the way of that. So I do appreciate your availability. All right. So this is the worksheet that we're going to be working on today. It's focusing on respiration and how that works. So the beginning says, how do we breathe and why do we breathe? This activity is designed to give you an understanding of how and why we breathe and some of the mechanisms that control the rates of breathing. How do we breathe? Explain the mechanisms of breathing. To do this, diagram or model and explain the general movement of oxygen and carbon dioxide into and out of the lungs, lung alveoli, blood, and tissues. Be sure to include all the following terms in your diagram. So here are the terms that we have. And to be able to really show all of this stuff, there is a couple of figures that I will be drawing on, so just ask questions when you guys have it, but if not, I'm going to go through each term, sometimes out of order, just depending on where they fit best. So starting with the diaphragm, I'm going to make this smaller a little bit, just so I can get the whole picture in there. The diaphragm is not pictured on this model, but it does sit right underneath the lungs, kind of like so. It's not the best drawing. Actually, let's just redo that all together. I had too much coffee. Now my hands are shaky. So this is the diaphragm. We can kind of check this off our list. In terms of diffusion, CO2 removal, demand, all that stuff, I'm going to be talking about that when I draw the flow of oxygen in and out. Oh, this is a lot of information on one photo. Sorry. Let me fix this. Okay. So the lungs are found right over here. And inside the lungs, we can find these little sacs called alveoli, and this is where the gas exchange occurs. Moving on to expired and inspired air, I'm going to be doing this with different colors. So the inspired air that goes through our nasal cavity and our mouth, so this is inspired, and also oxygen, because we breathe oxygen in. So we have expired air and oxygen, inspired, sorry. For expired air, I'm going to do that in pink. So this is expired, and this is carbon dioxide. And so this can also go with CO2 removal. And what we drew for that inspired air can also be just a drawn representation of the oxygen demand as well. And for diffusion, we have oxygen diffusing into, we're breathing in inspired oxygen, and that's going through our lungs, that goes through our, bronchioles, to the alveoli, and the alveoli is where diffusion of oxygen to the rest of the body occurs? So that's where we see that exchange of CO2 and O2. So moving on to the brain, CO2 sensors, medulla oblongata, that's all on the next page. The last two on this page are those lung tissue and skeletal muscle tissue cells. So lung tissue cells are obviously found here. Skeletal muscle cells are found on the ribs. They're kind of, you know how you have your ribs and you have the muscle on the outside. So this is where we're going to find our skeletal muscle cells. And both of these are very important for the exchange. And so that skeletal muscle attached to the ribs helps tighten and pull the rib cage up so that your chest can expand and then those lung tissues can fill with air. So those muscle cells are really important because that is what reduces the air pressure inside your chest. And because air moves from high to low pressure, that's how we can breathe in. So I'm going to talk about the brain, the sensors, and that exchange of these two respiration equations on the next page. So right here, this long stem, though it's not shown in the diagram, this is where the medulla oblongata is. And that's what's being shown also down below, this stem. Can you guys hear me and see my stream? Okay. Because the offline thing might be something on my end. I just updated the software that allows me to stream, and so I think it might have messed up my Twitch analytics. So Twitch analytics is not the right thing, but I think it messed up the connection with my Twitch account. So for sure, that'll be fixed by next week. I'm sorry. It happened just like a few minutes before I started. It was like totally blindsided. But thank you for letting me know that you guys can hear me, because that's my main concern. But also, if you're having trouble seeing and hearing this, there's always videos posted on YouTube. And if you really needed that extra credit point, just totally feel free to reach out to me, email me, and be like, I watched it. Okay, yeah. So the PSU sensors can be found within the medulla oblongata. And that's basically all found here. The medulla is really pivotal in evaluating your CO2 levels and adjusting your breathing. So we don't have to think about breathing all the time because of our lovely brain. But for example, you can pass out from not receiving enough oxygen. You can pass out from hyperventilating. And that's all done through those PSO2 sensors in the medulla oblongata. So I'm just going to put, there's peripheral chemoreceptors, other receptors. So I'm just going to write here, P receptors. And lastly, is what canceled? Sorry. And then finally, for the last thing, just while that's getting figured out in the chat, I'm just going to keep finishing this. So the last few things on that little checklist we had to do with these equations for respiration. So we have glucose or carbohydrate plus oxygen. It's broken into carbon dioxide, water, and energy. So I know I didn't do that much here, but that's basically the equation for why we need oxygen, because oxygen is the final electron acceptor in the electron transport chain, and that's where we get a majority of our energy is through that electron transport chain through oxidative phosphorylation, and that's the main driver of energy. So now we're going to move on to more questions, just describing respiration, different scenarios, and just getting a better understanding. So the first question says, explain briefly why we breathe, or more specifically, where is what we breathe in used in the body, and where is what we breathe out produced in the body. So what happens to the air we breathe in, and what happens to the air that we expel. The air that we breathe in supplies the cells for cellular respiration, so supplies cells with oxygen for cellular respiration. Remember, ultimate electron, this is just shorthand for electron acceptor in the ETC. And what we breathe out rids our bodies of carbon dioxide, which, as we saw in the previous page, is a waste product of respiration. And so the sugars in respiration get broken down into CO2 and water, and then we exhale CO2. Excel? I am not saying that word right. I always do this with my vocabulary. Expire CO2. Expel sounds like it did something too, like bad. Anyway. Sorry, I keep changing the size. Okay. 2. Oxygen is transported in the blood in reversible combination with hemoglobin. How does the level of CO2 in the blood contribute to the blood pH? So the chemical reaction for this is CO2 plus H2O can be converted into this, which is called carbonic acid. And that can further be broken down into this. And so how CO2 levels contribute to blood pH is that the more CO2, the more it is available to be broken down into this, which means that our hydrogen ion concentration is increasing, which means the acidity in our blood is increasing, which means pH decreases. So the more CO2 we have, the more hydrogen ions we have available, and that lowers our pH and it makes things more acidic. Alrighty, B. How does the level of CO2 in the blood affect the affinity of hemoglobin for oxygen? That is, how does concentration of CO2 in the blood change its ability to carry oxygen? And what is the Bohr shift? So I'm not sure if you guys have already talked about the Bohr shift in your lectures, but we'll see some examples of what that graph looks like on the next page with different questions. But the Bohr shift is that it's that graph that we're familiar with that looks like this and just describes the relationship between oxygen binding affinity and the concentration of carbon dioxide. So what the Bohr shift says is that hemoglobin's oxygen binding is inversely related to the concentration of carbon dioxide. So hemoglobin will have increased oxygen binding affinity if there is less CO2. and so forth. So the shape of hemoglobin changes in response to pH. So it can give up more of its oxygen at tissues than it would at its optimal pressure. Hemoglobin's able to give its oxygen to the right tissues than it would at a higher pH. So the more CO2 that there is at lower pHs, as we can see at this curve, then hemoglobin's going to give it up as faster than it would at its normal pH. Okay, is the Bohr shift more likely to occur after exercise or after hyperventilation, which is rapid breathing with no exercise involved? So exercise increases the amount of ATP required per unit time. So when we're working out, we need more energy, and that is obvious in comparison to no exercise. If we're sitting, we need a lot less energy available to our bodies than when we're moving or running or any of that. So ATP production via cellular respiration produces CO2 as a waste product. So the addition of more carbon dioxide that lowers the pH results in a conformational change in the hemoglobin to deliver more oxygen to tissues undergoing exercise. So we're going to see the Bohr shift more likely to occur after exercise than we would after hyperventilation. So the more CO2, the more hemoglobin is likely to give up its oxygen that it's holding on to, is the moral of the story. Wait, yeah, to the tissues. Okay, awesome. Now we're going to see some examples of oxygen dissociation curves. And so we can see here that we have a normal adult, just the regular curve, a reduced pH condition where we see the normal versus reduced. And then we're also going to look at a curve with a fetus versus its mother and answer some of those questions below. So I will be kind of scrolling up every so often just to reference the different graphs. So A is asking how the curves differ, and then we're going to dive into the specifics. First is normal versus reduced pH. So as we can see, if we're looking at this graph as compared to this graph, but we can just look at this because it gives us the curve for normal. So as we kind of talked about this in the last question, question 2C, where the addition of more carbon dioxide lowers the pH, and that resulting conformational change makes hemoglobin deliver more oxygen. So we can see how reduced pH would make this oxygen go relatively quickly versus on this red curve under normal conditions. And hello, no, I have not taken attendance. I usually do that like halfway through, but thank you for reminding me, so I'll put that in right now. Usually I'll put attendance in like 2:20, 2:30, and I'll put the form in a couple of times. Changes hemoglobin. Like during exercise. Oh, you guys can't even see what I'm writing. All right, the next question is saying infant versus adult. And so for this, we're going to be looking at this graph. And we can see here that the adult hemoglobin becomes totally saturated at a pressure of approximately 100 millimeters. So right here. But we can see in the fetus that it gets saturated at about 60 instead. And so the reason for this is that it allows the fetus to pull more oxygen from the mom's blood than it could if it had the same pressure. So fetal partial pressure saturation is lower than the mom's. Alrighty, and then kind of moving in with this question, what would happen if fetal and adult hemoglobin had the same affinities for oxygen? So basically, what would happen is if the hemoglobin of the mother and fetus had the same affinities, the fetal blood would never be saturated with oxygen, which is not ideal because then that transport of oxygen is going to be reduced, and so the metabolism of the fetus is not going to be as optimal as it would be with the most amount of oxygen it could get. So it could affect development. They could be underdeveloped or not even make it to term. So yeah, it's not good, and there's a reason why it's lower in fetuses than it is for the mom, which I think is so cool how just nature has been able to do any of that stuff. So yeah, let's write that down. Oh, you guys, I'm so sorry. I don't mean to keep doing this. I'm gonna, this like never happened to me last time and now I just can't get it in the page. But I will, thank you. Thank you very much. I really appreciate you guys in the chat. Alrighty. And so last question, actually in frame. If they don't get what they want, some small children threaten to hold their breath till they die. And, you know, people say that they don't want to have kids. I don't know why. Children who are very strong-willed may turn blue, but they will not die because they will pass out and the autonomic breathing response will take over. What types of control are involved in holding your breath? Why, for what physiological reason, will you pass out if you hold your breath for too long? I personally was never one of those kids. The determination that a kid has to have to pass out from holding their breath is honestly so funny to me. Like, I know that that's not okay because they're not getting enough oxygen, but that's really funny to me. Anyway, so in both cases, both holding your breath and hyperventilating, CO2 levels are going to change, and that is what's going to trigger the medulla of the brain that we talked about. So, exactly, sheer willpower. So if CO2 levels, let's say, increase, let's just say if they get too high, we'll start that. Then the medulla triggers a response that causes you to pass out. And because you're passed out, then the medulla can regain that involuntary control of the rate of breathing and then restore it. And then hyperventilating would actually reduce the carbon dioxide because you're pushing out as much. When you're breathing really, really fast, you're just expelling carbon dioxide. You're not taking in as much oxygen. So then this would decrease CO2 levels, and if it got too low, then the medulla would recognize it, and involuntary breathing would be re-implemented. However, if you force hyperventilation, so let's say the medulla has tried its best to involuntarily make you breathe at a normal rate, but you still have forced hyperventilation. This happens a lot, not a lot, not all the time, but I've seen it sometimes with friends. Maybe they're having a panic attack and I wouldn't say they're forcing, but it's all, the biological response is just to breathe, maybe force out over that normal rate of breathing because of those feelings of anxiety. That's just an example. And so it can cause the peripheral arteries to constrict, reducing the blood flow to the brain. And so that's what causes you to pass out. And then similarly to the last response, so breathing would stop temporarily. This isn't similar, actually. Don't know why I said that. But when you're passed out, it's similar in that things are restored. So in the increased CO2 levels, where we're holding our breath and that CO2 is building up, medulla responds, you pass out, it restores that normal breathing. However, for hyperventilation, where CO2 is being expelled and it's at critically low levels, what happens when you pass out from that constriction is that your body actually stops breathing for a moment to restore the CO2 levels and oxygen levels in your body, and then breathing will continue again. And by temp, I just mean temporarily. Okay, that was a pretty short one, but that is the only thing that I have for you guys this week is this worksheet. So before I let you go, I'm going to put the Google Forms in the chat one more time, and if anybody has any questions, I'm going to stick around for like 5 more minutes, if that's okay. But if not, please enjoy the rest of your day, get that extra credit, enjoy the sunshine before the rainy weekend. The types of control and holding your breath, it's just more of your control. So in terms of like the control involved in holding your breath was just you controlling your breathing. But if you hold your breath for so long that the CO2 levels rise to an unhealthy level, the medulla in your brain will kick in involuntarily and you'll pass out. And then the medulla will continue doing that involuntary job and it'll restore that breathing pattern. I guess you could say it's skeletal muscle just because that's what, like, that's what you breathe with is the skeletal muscle around your ribs that increases your lungs, which decreases the air pressure. So you just kind of be holding those tissues steady, like not really using them. I hope that makes sense. Okay, awesome, cool. Yeah, thank you for the question. Oh, you guys, seriously, thank you so much for everything that you guys are giving me because I've never used Twitch before or anything, and so I always forget. Like there's a bunch of little details like that with like the description and other stuff that needs to be updated. So thank you so much. I'm gonna fix that about right after the stream, and have a great rest of your weekend. I will see you next week, not on Thursdays at 6 p.m. Thank you. Okay, bye guys. Have a good rest of your day.